All right, welcome students. We are going to be talking about recursively defined sequences. Okay, so we've seen explicit equations before. So an explicit rule is going to give a of n this function of a sequence as a function of the term's position n. So a kind of representing the value in the sequence and n which number within that sequence. Okay, so in this case, in this sequence they're giving a of 1 is 3. It's the first term in the sequence, and so on and so on. And we can generate any number in that sequence. If I want to know what the 100th term in the sequence is, I can take the equation that they're giving right here and just change n to 100. And this is going to tell me what the 100th term of this sequence is going to be. So that is what explicit rules do. But what we're going to focus on today is recursive. Okay, so a good example of what recursion is if I were to ask you to tell me what salt tastes like. There's pretty much only one answer to this, and that is that salt is salty. We call this type of definition a recursive definition. We are using the word itself to define the word. So when we talk about recursive functions, we are talking about a function that refers back to itself. All right, so that's going to be new and weird, but follow along and we'll try to make this simple. So the recursive equation for an arithmetic sequence. Remember that arithmetic is all about adding or subtracting some common difference over and over and over. So we have our function, a of n. Now we are saying what a of n is in terms of that same function. Okay. Now if n is the number we're looking for, then n minus 1 must be the number that came right before it. All right. So what this is saying is to find the nth term of the sequence, go to the number before it, and just add the common difference. Okay, but we are using our function to define our function. Okay, now that is how arithmetic sequences are going to work. We're just going to add that common difference to whatever the previous number had been. For a geometric sequence, geometric sequences kind of work by this repeated multiplication or division. We are multiplying that common ratio. So once again, I've got my function a of n, and I am defining it using my function a again. So to find the number n, I need to find whatever n minus 1 was, and then multiply by the common ratio. So these are recursively defined functions. I am using the function a to define function a. All right, so let's see this in action. We're going to write the first 6 terms of each sequence, and we're going to do this based off of the recursive function that they've given us. And then we'll go ahead and graph what is happening there. So let's start with this one. We know that the first term is 2. Okay, great. So my first term is 2. And in fact, let's go ahead and do this as a table, 3, 4, 5, and 6. All right, so those are going to be n, and these will be a sub n. So we know the first term was a 2. Now, here is where it tells me how to find the next one. So if I want to find a sub 2, that would be our next one. This is telling me, well, find a sub 2 minus 1. Or in other words, find a sub 1. Well, I know what a sub 1 was. It was a 2. And then add a 3 to it. So adding 3 to 2, I would get a 5. Remember, this function is always just going to tell me to take, if I want to find one term, I need to go to the term before. All right, so to find the third term, let's see, the last one was a 5, add a 3, 8. All right, to find the fourth term, go to the third term, 8, add a 3, 11, and so on, and so on. And that's what the recursive equation is telling me to do. Simply add the 3 to the previous term. Okay, and then we could draw a quick graph, 2, 3, 4, 5, 6. All right, and let's say that's 2, 4, 6, 8, 10, 12, 14, 16, 18. So the first one was at 2, then at 5. Now my lines are not perfect because we're kind of just sketching these, but even with my poor sketch, one thing we should see happening is we should be able to still see the approximate shape of this, which is coming out to be a line. Okay, arithmetic sequences are linear. All right, let's look at the next one. So n, a sub n, 1, 2, 3, 4, 5, 6. All right, so as I am looking at this, I notice that they told me the first term was a 1. Great. The recursion tells me to find the next term, I need to go back to the previous term and multiply it by a 3. Well, the previous term was 1, multiplied by 3 is 3. Now the previous term to the third is 3, multiply it by 3. Previous term to 4 was 3, it was a 9, multiply it by 3. And continue. Okay. All right. And then if we graph these, for the sake of keeping this video short, I'm not going to do all of it. But essentially what we're going to see is it starting out very small. We only went from 1 to 3, but then 3 to 9, and then to 27, and to 81. Okay, so not a perfect drawing, but we would see the increases started out very slow and then started going up. The rate of change increased. And so we got this curving exponential. Okay, so now let's get into the business of figuring out how do we write these recursive rules. Notice something both of these had in common. Both of them started by telling us what a of 1 was. So I'm going to start with that. All right, so my first term here was a negative 30. Great. Whoop. And the first term of the second one was 500. All right, great. So I've got those. Now, there is a difference between arithmetic and geometric, depending on whether or not I'm adding a common difference or I'm multiplying by a common ratio. So we got to figure out what do we have. So let's see, how do we go from 30 to 18 and negative 18 to negative 6? What we can do if we're not sure, since these are kind of tricky numbers, is to go ahead and just use our subtraction going backwards or our division going backwards and see what kind of gives us a consistent value. So going backwards here, 18 minus a 6. 18 minus 6 is going to be 12. 6 minus a negative 6, 12. Negative 6 minus an 18, 12. Negative 18 minus 30, 12. We added a 12 every single time. So to find any number, a sub n, what I need to do is I go to whatever the previous number was, a sub n minus 1, and I add 12 to it. And there's our recursive equation in full. All right, so let's try that over here. 0.8 minus a 4 is going to be negative 3.2. 4 minus a 20 is negative 16. I'm not getting consistent numbers from that. So I'm going to bag that idea. Okay, let's try 0.8 rather than minus. Let's do a division. So 0.8 divided by 4 is going to be 1/5, or 0.2. Okay, 4 divided by 20. And in fact, so we can just use the decimal. 0.2. 0.2. 20 divided by 100. 0.2. Okay, 100 divided by 500. 0.2. So we were multiplying by a 0.2 every time. 500 times 0.2 would give us 100. 100 times 0.2 would give us 20. So now I know that to find any number in the sequence a sub n, what I need to do is go to the previous number and multiply that by the common ratio, 0.2. Okay, so now let's translate. We've already seen explicit rules. Can we figure out the recursive rule from the explicit? Or can we take our recursive rule and then figure out what the explicit should have been? All right, so first let's notice what this one is doing. It's minusing 10 each time. This must be arithmetic. All right, so if it's arithmetic, then my equation, my explicit equation, should take the form a sub n is equal to a sub 1 plus the common difference multiplied by n minus 1. All right, so let's see if we can find some of those values here. Well, a sub 1, they told us right out. So great, I know that's going to be a 25. Plus, now I need to find the common difference. Well, the difference is right there. They told us. What do we do every time? We minus a 10. So I'm going to go ahead and change this rather than plus d. I'm minusing 10. How many times do I minus 10? And minus 1 times. Great. So we found our first term and the common difference. All right, let's look at this next one. We notice we're multiplying here, so this is going to be a geometric. All right, so for geometric, the equation should look like a ace of n minus 1 being multiplied by the common ratio n minus 1 times. Okay. All right, well, once again, they told us what the first term was. So 19.6. Now we're going to multiply it by the common ratio. So what were we multiplying by? We multiply it by a negative 0.5 every time. and we're going to do it n minus 1 times. All right, so straightforward. We can find all of our information for the explicit rule right out of knowing the recursive. How about the other way around? So write a recursive rule for each explicit rule. All right, so we've been given an explicit equation. For my explicit rule, or for my recursive rule, I'm first going to need to know what a of 1 is. I need to know the first term. Not quite as clear here because they didn't write it in the way that we're familiar with. So that makes it a little bit tricky. But don't forget, ace of 1 is just what is the first term. And this equation is built to tell us what the value of each term is. So if I did ace of 1 is equal to negative 2, this should tell me my first term is a 1. I just needed to plug in the values and use the equation to find out what that first term was. Now, this is a linear equation. It's mx plus b. Linear equations are always going to be arithmetic. Okay? So how is the value changing? Now we could do things like I could find ace of 2 and ace of 3, and we could look for each of those. But there is an easier way to figure out how this will change. Every time n goes up by 1, remember we're multiplying this by a negative 2. It means there's going to be another negative 2. We're going to minus even more negative 2's. So that is my common difference. So ace of n, I'm going to have, what I do is I take the previous term and then I minus 2 from it. And we could quickly verify. So let's see, if I am correct that we started at a 1 and then we take away a 2 every single time, the next value should be a negative 1. Well, if I put that into the equation, so 2 or a negative 2 times 2 with a plus 3, so that'll become negative 4 plus 3 is negative 1. It's exactly what my recursive equation thought it would be. So yeah, I verified that my thinking was correct. I correctly identified the common ratio. All right, let's see. This one is written in the form that we're familiar with for geometric sequences. So I can tell that the first term was a negative 3. Now we're going to take, to find any number, we take the previous number, ace of n minus 1. We then multiply it by r. Okay, and r was 2. And there we go. All right, so let's look at some more complex sequences. This is a famous sequence. I want you to take a moment, try to think if you can see the pattern in it. This is called the Fibonacci sequence. A little bit of a challenge, isn't it? How did a 1 just stay a 1 and then it turned into a 2? So what makes this one interesting is the way that we kind of have to reference it twice. So I'll show you. 1 plus 1 is 2. And 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. And so on and so on and so on. So we need to figure out how are we going to write a recursive rule for this sequence. Now I'm going to go ahead and use a function notation. And I said this was the Fibonacci sequence, so let's go ahead and use f. Okay. Well, so what is our first term? Well, the first term was a 1. So now how do we figure out for any term x? Now, I want you to be noticing I'm using function notation now, but it's still very similar to that sequence notation that we've been using, and I will write it in a sequence notation, but I want you seeing how these two are similar. Okay, so let's think about what we did to get 3. Okay, well, first I took the number from 2 times before. So I want to figure out what was 2 times before the xth number, and then we added it to the number that came just before. Okay, to write it in the notation we've been doing, it's like a sub n. And we could say that we wanted the number 2 times before, and we add it to the number that came just before n. Okay, so what are the next 3 terms of this sequence? Well, let's go ahead and continue it. So to get past 8, we need to add the 2 numbers that came before, so 5 and 8. So after 5 and 8, we would get 13. So now we do 8 and 13 is 21. 13 and 21 would then add to 34. All right, I hope this was helpful. Good luck on your assignment.